Hello, my name is Ribo Liu. Today I'm very happy to introduce our work accepted by AAAI 2021. The paper name is Mitigating Political Bias in Language Models Through Reinforced Calibration. The motivation of our work is we find GPT-2 is actually politically biased. We know that given a writing prompt, we can generate human-like tasks with language models. In this case, I'm from Massachusetts, I will trigger generation Hillary Clinton as blah, blah, blah. Although such generation could be human-like, it's definitely politically biased. Such bias heavily depends on the demographic attributes in the writing prompts. In this case, Massachusetts, which is the blue state name in the United States, could partially explain why it generates Hillary Clinton as a continuous. Since the demographic attributes and topic keywords play key roles in political bias, in this work, we study three kinds of sensitive attributes: gender, location, and topic. For each attribute, we also prepare actual options. The options are described by keywords we collected from publicly available data. For example, the male option in gender attribute is described by 17 male names. Blue states in location attributes are the blue states names as recorded by the 2016 United States election results. With these option-related keywords, we can actually fill them into the writing prompts to study their effects on generation bias. We find all generation exhibit bias. The conservative writing prompts can even trigger liberal-leaning generation. Such bias can be a severe problem if we deploy language models in real-world settings. For example, dialogue systems, machine translation system, and other real-world AI settings. Because the political bias perpetuated language models can be propagated to downstream tasks. So in this work, we define two bias metrics: indirect bias and direct bias. First, let me introduce the definition of base rates. It's a probability of a sequence Y that is triggered by writing prompt X being classified as liberal. Here, the liberal is denoted as class 1. If we denote the sensitive attribute as A, in terms of conditional independence, if the probability of the sequence Y being classified as class 1 is independent of the field attribute A given the writing prompt X, we say the events Y equals to 1 and A are conditionally independent given the writing prompt X. In other words, if the attribute A has strong effect on the classification probability of the sequence, we can tell the attribute can lead to bias of language model generation. So the indirect bias can be computed as the difference of the above two probabilities. We name it indirect bias. However, sometimes we deliberately want to generate some bias text. For example, I am a Democrat. About voting, I will blah, blah, blah. Here, I am a Democrat. About voting, I will is actually a liberal-leaning writing prompt. Ideally, liberal-leaning and conservative-leaning prompts should trigger equal bias. So, we define direct bias, which is the difference in the extent of bias between liberal-leaning and conservative-leaning writing prompts triggering in terms of indirect bias. We name the difference as direct bias. So here, we show the writing prompts we prepare for each attribute. We have 30 writing prompts in total, and they are categorized for indirect and direct bias study. Next, we present how to do language model device through reinforced calibration. In this paper, we present two modes for language model device: word embedding device and classifier guided device. Our advantages are we do not need to collect more balanced data, and we do no change on the original language model architecture. We first introduce DBus reward. It's composed with three parts: vanilla policy, which is the output of the softmax layer; DBus policy, which is the updated policy based on DBus calibration; DBus gain from either of the two modes, word embedding device and classifier guided device. For mode 1, word embedding device, in each step generation, we try to control each step pig token has equal distance to the two groups of salient words, liberal and conservative. The distance is computed as the negative similarity of word embedding and current step hidden states. WL and WC are the salient words groups used by liberal leaning group and conservative leaning groups, respectively. For the second mode, we use the latest three steps of accumulated hidden states as a reasonable estimation of the current generated sequence. We first train an external classifier and use that classifier to judge the bias in each step generation. R is the modified cross-entropy loss that we use to get the reward of current step classifier-guided device. Here, we show the full algorithm of our reinforced calibration. We first compute the DBus gain from either mode 1 or mode 2. And then we compute the DBus reward with equation 7. Finally, we update the current step policy to obtain the DBus policy. For the evaluation, we first consider the automated one. As shown in figure 2, figure 2A and B are actually the UMAP 2D visualization of 5,606 sentences generated by vanilla GPT-2 when the sentence embeddings are encoding output of A, not a pre-trained XLNet classifier; B, pre-trained XLNet classifier on media cloud dataset. C and D are visualization of DBus sentences by mode 1 and mode 2. The embeddings of C and D are both from pre-trained XLNet. We mark the class of each sentences labeled by the pre-trained XLNet classifier. A and B show the clustering result of whether or not we provide the classified label of XLNet for each class, for each sentences. We find the major of these sentences are liberal leaning, and they can be easily separated by UMAP clustering. B, C, and D show before and after we perform DBus on the sentences. C is DBus with mode 1, word embedding device. D is DBus with mode 2, classifier guided device. It shows that the sentences are hard to be separated even given the actual labels predicted by the XLNet classifier. After the qualitative evaluation, we also conduct a quantitative evaluation. We compute the indirect and direct bias of all options in 3 attributes. We find certain options exhibit more bias than others. For example, the female option in gender attribute, rest state option in location attribute, immigration option in topic attribute. And in general, classifier DBus perform better than word embedding DBus. But in the highlighted options, we see the word embedding device sometimes can decrease more bias. Also, in some cases, we find word embedding device sometimes fail to decrease the bias. We also study the trade-off between d-bias strength and perplexity. The d-bias strength parameter lambda starts from 0, which means no d-bias, is from the vanilla generation of GP2, and it gradually increases to 0.9, which is the strongest d-bias. It shows more strong d-bias will lead to higher perplexity, which means the generation is less fluent. About related work, in the left table, we list whether the method needs extra data, more training, and type of bias it studies. In the right table, we compute the bias after we use the method from our side and from related work. Our method requires neither the original training data nor retraining the model from scratch. And to the best of our knowledge, we are the first studying political bias in generative language models. Compared with prior arts, our method is more effective. The perplexity of our d-bias generation increases slightly because we are generating text from scratch rather than just simply replacing some tokens, which is used by Ian Glove, which is a prior art, which is a state-of-art method on the market. We also conduct human judgment evaluation. We study 3 perspectives: d-bias, which means how much d-bias after using our method; readability, how fluent our d-bias generation; coherent, which means whether or not our d-bias generation is still coherent to the writing prompts. We find that our d-bias method indeed decrease the bias and also keep the same level of readability and coherence as the baseline sentences. As a conclusion, first, we define what political bias is in generative language models and present how to mitigate such bias during the generation. Second, we present 2 modes of d-bias: word embedding d-bias and classifier guided d-bias. The advantage of our method is we do not need more data, and we do not need to retrain the language models. The limitation of our work is we only focus on binary type bias. Other kind of bias, for example, emotional bias, which typically has 9 types, we may need non-trivial modification on our model to apply for that kind of bias. Thank you. If you have any questions, please send your questions to my email. This research was supported in part by the Dartmouth Berg Research Initiation Award and Amazon Research Award. Thank you very much. Bye.